Hi everyone. Thanks for attending session 3, which is on power and cost efficient clouds. We have 3 papers that will be presented in this session. The first paper is about leveraging application classes to save power in highly utilized data centers. This will be presented by Kostis, who is a PhD student in electrical engineering at Stanford University, and advised by Christos Kozirakis. His research interests lie in the area of scheduling for low latency data center systems and networks. Prior to this, he completed his diploma in electrical and computer engineering in the National Technical University of Athens, Greece. I will let Kostas take it from here. There will be a short, about 3 to 4 minute presentation, followed by a longer, about 10-minute Q&A. So please feel to go ahead and type your questions into the Q&A button here, rather than the Hoover app, so that I can just read out your questions and we can take it from there. Great, Kostas, go ahead, please.
Okay, thank you very much for the kind intro. So today I'm going to talk about Pact, a system that we built at Google that allows us to save power even in highly utilized data centers. So before we dive deeper into Pact, we need to see the environment in which it has to operate. So the Google environment is quite complex. The tasks are actually running either as best effort or latency sensitive jobs, which have their own SLOs. But the thing that we need to keep in mind is that the LS SLOs are very tight and must not be violated. And moreover, the machine utilization in Google is quite high. And this is achieved by packing the best effort and the less tasks in the same set of servers or even cores. So in order for any power savings solution to be effective, it must manifest at a wide utilization range. And finally, the cluster scheduler and the operators, they have no visibility in the application level metrics. And that means whatever power saving solution we build, it must follow an application agnostic or opaque box approach. The only thing, sorry, that's the timing. The only thing that we know about each individual task is whether it's a less or best effort. So now let's see how Pact works. So Pact or a per application class a turbo controller consists of 2 separate mechanisms. The first mechanism is turbo control, which basically uses a DVFS in order to throttle only the best effort tasks without affecting the latency sensitive ones. And it achieves that by adding a new kernel patch that switches the operating frequency of its CPU at the context switch of the kernel already in the Linux scheduler. And the second mechanism is a CPUJailing, which executes the latency sensitive and the best effort tasks on separate sets of cores, offering isolation and maximizing the power savings achieved by turbo control. So this is like a snapshot of the results, where we plot the average machine power consumption in a cluster at Google over the machine utilization. So we bucket the machines by utilization, and we measure the average power consumption for each machine in each utilization bucket. And here we test 4 different configurations. The baseline is whatever was used before at Google, which does not differentiate between the BA and the LS tasks. The Pact is the final solution that we build, and we also examine each individual mechanism by itself. So here we can see that even though at a low utilization, a turbo control by itself is effective, at high utilization, CPUJailing is needed in order to run the latest sensitive and best effort tasks in separate set of cores, and thus allow turbo control to be effective and to be able to throttle only the best of our tasks and save power for utilization as high as 85%. And that's how we achieve our goal of reducing the power consumption without affecting the LS performance. And we have many more results and analysis in the full talk and the paper. And I'm happy to hear your questions.
Great, thank you so much. We have 3 questions that were posted in the Hova app earlier. If people have more questions, feel free to type them out in the Q&A bar here. So your first question is, have you considered restricting the CPU jail to a CPU socket, which can yield further power savings, since the voltage of the entire socket can be lowered if the cores are operating at a lower operating frequency?
So that's a good question, but actually in our setting, it doesn't make much sense to do that. The first reason is because it's very uncommon for the CPU utilization to be less than 50%, and hence for all the jobs in the machine and the buffer that we mentioned in the paper to fit in one socket, so that we do this optimization. And the second reason that we don't do that is because, let's say that we run them on separate sockets and then we consolidate them in one so that we can turn off the frequency, like on the second socket. In that case, the tasks that moved from one socket to another, they will have to do remote memory accesses, which is much more expensive than the local socket memory accesses, and this will affect the performance.
Do you think that, so when you are moving things to a different socket, you mentioned that you might compromise your
Locality.
Right? But then oftentimes, I mean, people are starting to move towards disaggregated memory systems. So wouldn't the cost be pretty much the same as contacting like a disaggregated node?
In the future, yes, but that was not the situation at Google while I was interning there, and I built Pact. So I agree with you that, like, if all memory access cost about the same, it makes a lot of sense to do this optimization.
Okay, cool. I learned a cool insight there, but cool, thanks. Second question again from the Hova app is, have you considered restricting the CPU? Oh, sorry, I think that was just, sorry. Another person says this is interesting work. Do you think you will be able to apply similar principles to other hardware components besides the CPU, i.e., that is memory subsystem or storage subsystem?
So I'm not the expert on how the memory like on the internals of the memory or the disk subsystems, but if it's possible to tune the power consumption at a very fine scale, then I don't see any reason why not. And in terms of scheduling, not of power consumption, I think that there's already work on that, on how to like schedule those at very fine scale. And then if you have that as a building component, then you might be able to tune the power consumption as well. So yes, I think it's feasible.
Can you speak for the, you do compromise some of the performance in terms of tail latency, right?
Sorry, what do you say? That we compromise some of the performance in terms of tail latency. So look, the workloads that we care about the tail latency of are the latency sensitive ones. And ideally, we do not affect them at all. And the way we tested that is there was like a huge workload that was deployed in the data center that we tested Pact on, a latency sensitive workload, which actually ran on thousands of machines. And then we compared the latency histogram between the machines that run on the baseline configuration and the Pact configuration, and they were identical. And the latencies were like in the orders of tens to hundreds of microseconds. So we're confident that the tail latency is not affected.
Great, thanks. This is really interesting work, and I look forward
Thanks.
to reading the paper. Those are all the questions that we have in both Hua and Zoom. So if you can stop sharing your
Sure.
screen. Oh, I'm being told that there's one more question that I
Sure. Yeah.
uh,
Have to answer.
but I mean, I don't see the
Cannot
question,
find it.
and I think we are at the 8:15 mark. So if you don't mind,
Okay, I can
and if
answer it on Huva if it's there.
you can answer
I'll
it on
answer the
Hua,
final.
it would be great. Thank you so much for presenting.
Okay, thank you very much.
Um, Oops. Okay. So our next talk is called PFAL, in-application CPU scheduling to reduce power consumption of in-memory key value stores. This talk will be presented by Shoan Ismail Asiapi. I'm sorry if I pronounce your name wrong, who is a third-year PhD student at Boston University. He is advised by Professor Azar Vestavros and Professor Vasia Kalavri. His current research focuses on designing and building efficient system software for big data and stream processing. He's planning to participate in an internship program in the summer of 2021. All right, let me just start slideshow and then you can start presenting.
Hello, everybody. Thank you for the introduction. So there are many applications with high fan-out that rely on key value stores. Key value stores have diurnal pattern. For example, this figure shows a workload in a Facebook data center that has a diurnal pattern. Service providers provide for peak load to ensure tail latency. Therefore, the problem is high energy consumption of in-memory key value stores. There are some solutions that could possibly be used to save power for in-memory key value stores. For example, idle state governors. Idle state governors, if they predict that the CPU is gonna be idle for a while, they turn off some component of the CPU to save power. For example, we have C0 operational node, C1, C1E, and C6. C6 is the deepest idle state. If the CPU is going to be idle for 600 microseconds in our CPUs, the CPU go to C6, and a notable power can be saved in C6. But the problem is high arrival rates of workload in key value store fragments the idle periods to a very short idle cycles that prevents approaches that rely on idle state governor to save notable power. Another approach is feedback-based controllers. Feedback-based controllers monitor the load and they measure the latency or the load to a predefined threshold, and then they right-size the number of allocated cores based on their measurements. The problem with this approach is they're too slow, like operating at second intervals. Therefore, they can aggravate the tail latency. And then rely on operating system scheduler. Operating system scheduler like CFS operates at milliseconds interval. Therefore, they can increase the tail latency. And then the final approach that people use is DVFS and request delaying. They slow down the request when processing to like save power while meeting the deadline just in time. As we will show in our experiments, high arrival rates of the workloads in key value stores and short service time and high target latency prevent these approaches to save notable power. Next slide, please. Next slide, I think. Oh, yeah. So we designed PFAL to save power in memory key value store. we transferred the schedule, logically transferred the scheduler to the application. We pin the key value store threads to distinct CPU cores. Therefore, we eliminate the impact of the OS scheduler on tail latency. Inside the application, we do scheduling. One thread is responsible for scheduling, and all other threads that are called worker threads are responsible for serving user requests. The worker threads, while serving user requests, they learn about the load. For example, the peak load, the comment load, they share this information with the scheduler. Using this information, the scheduler threads identifies the off-peak periods. Over the off-peak periods, the scheduler gradually consolidates the loads among fewer number of cores. The remaining idle cores can save power by going to deep idle states. On the other hand, when the load approaches the peak load, the worker threads, independent of the scheduler, can send connections to distribute connections among increase the number of working threads. Therefore, in p-file, the scale down is gradual and scale up is fast. The top right figure shows the power consumption of p-file compared to memcached for a Google trace. As you can see, p-file can notably save power by up to 36%. And then we compare p-file to existing approaches like Rubik, which is a DVFS approach, and microDPM, which is a request delaying approach, and an optimal CS-state governor in simulation. This optimal CS-state governor has Oracle foreknowledge about future idle periods. We wanted to show how with this governors, how much these governors are going to be effective if one realized one day. As you can see, p-file notably outperformed this approaches, even the optimal idle state governor. Thank you. I'm happy to take questions. I can hear you.
Oh, sorry. Again, please type your questions into the Q&A. Meanwhile, I'm going to go ahead with a couple of questions that were asked in the Hoover app. So the first question for you is, were you able to measure the frequency switching latency? If yes, how did you do so?
Well, actually, so the p-file, it does not depend on DVFS. We do not use like DVFS or frequency in p-file. So we use like DVFS in like the other approaches use DVFS. So we use this latency for our simulation result. So we rely on other people's work, related work for this number. We didn't measure the DVFS latency.
I see. Okay. And your next question is, how would p-file compare against Shenango, which was published in NSDI 2019, which is able to change the core allocation of each application as often as every 5 microseconds?
Yeah, that's a good question. Well, Shenango uses like a DPDK, and it's able to achieve like a notable, much more higher throughput and low tail latency. But the thing is, fast core allocation, actually, it's not good for power. So the key to save power is to unbalance the load and let the cores to be idle for a long period. For example, 600 microseconds to go to deep idle state. But fast core allocations prevents this, like the cores going to be in an idle state for a long period. So our approach is different. We think that although like Shenango achieves a very good throughput, but this approach, I think, is not good for power.
So did you compare against that as a baseline?
We didn't compare because, well, Shenango's approach is not about power, so it's about like raising CPU efficiency. So we didn't compare Shenango to our approach because they were not working on power. Actually, they were like working on raising CPU efficiency by co-locating compute intensive workload like with latency sensitive workloads.
All right, so I have a question for you. I can see how this technique will work really nicely when you have these gradual diurnal load variations in a data center. But then what do you do when you have a load spike, when you have, say, maybe an important news event? So your load just spikes up and then you go back down. So wouldn't you end up with an oscillation effect because you would keep back and forth in terms of turning off and turning on your cores?
Yeah, well, that's a very good question. Well, the thing is, the packing or consolidating the connections in people is very slow. Like, actually, in our implement, every 1 second, we send the connections to we packet connections, and then it's coordinated with the scheduler. So it's very gradual, very slow to make sure that we're not gonna like drastically increase the load of one worker. And then if you see the situation that you just said, that a worker sends connections to their home, like we stop scheduling for like 30 seconds to make sure that we won't end up the situation that we send packing and unpacking connections.
So the load detection is actually time-based?
Yes, like every 1 second we measure the load and we share it with the scheduler, and the scheduler very like slowly packs the connections.
I get that, but when you're talking about how you measure the load ever so often, the load measurement itself is done with a timing window. I'm guessing you're doing interarrival rate distribution measurements, and that would be done within are you doing it within a timing window, or is it event based where you look at the number of requests that your application gets?
It's a timing window, like every 1 second, how many requests we get over the like past seconds. That would be the rate of the current load.
Okay, great. I guess if anyone has any more questions, feel free to type them into the Q&A window. And in the meantime, I guess I'm just going to continue asking you a question about the load transient, because I guess that's a condition that I'm particularly curious about, because let's say you have a load that ramps up fairly quickly because you don't want to miss the spike that happened in your measurement duration. So I'm wondering if you have any thoughts on how you want to overcome that.
So the thing, so you're saying, so imagine we have a load, right? So we know what is the current when a load, right? So, but whenever we get a new request, we have a counter, we know that what is the current load. So if the workload like significantly is increased, like for example, by 2 times, we actually, so if your question is, if you wait for that timing, saying like 1 second to send connections, how we do not wait for that. Because every time we get a request, we update the counter so we know, and we already have the current load of the worker. So if we we see a significant increase, we send connections home. So that's why we can keep microsecond scale tail latency. So we did this approach because every second we share the information with the scheduler, because we didn't want to have like overhead, or we wanted to keep the tail latency at microsecond scale. The scheduler is very slow, and its decisions and its packing. But when we want to scale up things, we are very fast. We were not waiting for the scheduler or that 1 second measuring thing that we have.
Cool, thank you so much. We have one more question. This was cross-posting from Hova on behalf of Brian Kim. The person says, interesting work. Can you comment on how PFAL would behave under heterogeneous workloads with different latency targets? Example with interactive versus batched.
So the thing is, we do not consider any we do not use any target latency with SLA information for PFAL. So PFAL learns the peak load, the load that is the maximum load that offered to the key value store, and then it identifies the off-peak periods when the load is not at peak, and then when it's identified the off-peak periods, it's consolidated the load among fewer number of cores. So the good thing about PFAL is we do not rely on third-party like users when to give the people SLAs when to save on the power. But if we like incorporate SLA for future work, we might be able to save more power.
Yeah, that makes sense. But I guess in the real world, SLA is also like very loosely defined depending on the application. So it might be hard to incorporate that because oftentimes it isn't always just a strict, oh, it's like a 300 millisecond thing. It's sometimes, oh, only 5% of requests, cannot violate a certain constraint or something like that, right? So I think that would be an interesting avenue for future work if you were to consider those different points in the SLA as well into your design. Cool. Thank you so much for your presentation.
Yeah, thank you so much.
I'm going to move on to the next one. Let me just bring it up. All right, so our third talk is called High Availability in Cheap Distributed Key Value Storage. Thomas is a PhD student at Carnegie Mellon University, advised by Dave Anderson. His interests lie in distributed systems, fault tolerance, and new technologies. Let me just bring up the PDF, Thomas, and then you can go on to start presenting.
Okay, thank you. Thank you for the introduction, and thank you everybody who for showing up to this session, which is a little bit late in the evening. So the problem that we're trying to solve, or I suppose the goal of this project, is achieving high availability at low costs in main memory class distributed storage. And we want to do this by using non-volatile main memory, which I'll be referring to as NVMM, as the primary storage medium. So the key to achieving high availability in this case is fast recovery. And this fast recovery is sort of complicated by the introduction of NVMM. So why is it necessary to rethink a recovery protocol just to use NVMM? Well, the performance characteristics of NVMM, which in some ways are similar to DRAM, have some key differences that add new opportunities and challenges when we're building fault-tolerant distributed storage. NVMM has very similar latency to DRAM, which would allow it to be used for the same low latency workloads. And it provides this with higher density per DIMM at a lower cost per gigabyte. So it's a very attractive proposition. However, this comes at the cost of slower reads and, more importantly, slower writes. So in other words, there's going to be more data stored per node and less write bandwidth to copy data after a primary failure. This is what complicates the recovery, and it makes failures dramatically worse. Our system, which we call Candy Store, enables fast recovery despite these limitations, and we do this while maintaining the cost efficiency of storing backups on SSD. Systems such as Microsoft Farm from Microsoft Research can achieve very fast recovery after primary failure, but they do so at the cost of maintaining multiple potentially expensive in-memory copies. On the other hand, systems like RamCloud, which use offline recovery, rely on fast parallel ingest of logs from SSD, and they fully replay these logs offline before resuming operation. This approach becomes a little bit difficult when there's more data and less throughput to recover it. May I get the next slide, please? In our system, we use what we call an online recovery protocol. This means that we resume serving client requests before all data is copied into NVMM from the SSD backup. This will cause some performance degradation during the recovery process, but our observation is that as long as the system is able to meet its SLOs, we consider the system to be recovered. Importantly, we observe first that real workloads have skewed request distributions, and second that SLOs usually include some amount of performance headroom. We take advantage of this workload skew by prioritizing popular keys during recovery, and we take advantage of the SLO headroom by prioritizing the recovery of just enough of these popular keys to enable the system to operate within SLO. And in the background, based on client requests during the recovery process, we demand fetch non-recovered keys from the SSD backup node. And of course, we have to restore full fault tolerance and performance to the system eventually, so we recover large batches of the least popular keys in the background. In our paper, we describe the various optimizations and techniques we use to make this online recovery feasible. For example, the hot-cold tiering of our backups. On the right side of the slide, I have a selected subset of our experimental results. These are collected on a 3-node cluster, which was generously provided by Intel. So we're running the YCSB-C workload with the Zipfian request distribution. And given a particular 99.9th percentile tail latency SLO on the x-axis, we measure how long it takes the system to achieve that SLO on the y-axis. In other words, in this graph, the time to repair, or TTR, for a 99.9th percentile tail latency of SLO of 250 microseconds, in our case is 8 times faster than the equivalent offline recovery protocol running on the equivalent hardware configuration. So in summary, our online recovery protocol can achieve significantly lower TTR than offline recovery running on the same hardware. And this will potentially enable the use of NVMe as primary storage in main memory class distributed storage. And this, in turn, potentially allows for significant cost and power savings, as well as the ability to store and serve larger data sets at low latency. Thank you, and I'll take questions now.
Great, thank you so much. So I don't think there are any questions in the Hova app. So people can feel free to post questions in the Q&A here. In the meantime, I want to ask you some questions of my own. So actually, it's really nice that you are addressing the issue of availability when the primary fails. I don't think I've quite seen that in other prior work. So that's really nice. But there are some things that I've been wondering about. So for example, how do you figure out when to trade off proactive recovery with application rights, or live recovery with priority pull and application rights? How do you strike that balance, and how do you make that decision about that balance?
So typically during the live recovery, the expectation is that there's going to be sort of enough capacity in the system that we can comfortably serve application rights without completely abandoning proactive recovery. Though I suppose the proactive recovery that you're referring to doesn't actually occur at the same time as the the application rights. So I suppose the idea behind proactive recovery in our work is that there's going to be some amount of time between the detection of a failure, or between the actual failure and then the point where you're sort of in the state where the client is actually sending requests to the primary. And we just wanted to take advantage of that time to sort of take a guess at whether we need to recover or not, and try to get as much recovery done as possible and make the most efficient use of that time as possible. I'm not sure if that answered your question, but.
Yeah, that makes sense. I had a couple of follow-ups, but then I see questions in the Q&A, so I just go over to that. Christopher Kennel says, nice paper. We're cross-posting from Hoa. But for your evaluation, you run on a 3-node cluster. Does the lack of cluster-level parallelism unfairly handicap the RAM cloud or primary backup comparison?
Yeah, so the question is, in RAM cloud, what happens is you use cluster-level parallelism. So if you have for example, a cluster with 128 nodes, you would sort of take the recovery and split it roughly evenly across all of those nodes. And in our evaluation, due to lack of hardware available, we only used a 3-node cluster. That is a good observation. That is a correct observation that running on a 3-node cluster is disadvantageous to RAM cloud style sort of massively parallel recovery. But sort of what I believe is the bottleneck in the recovery process is going to be the write throughput of the NVMe DIMMs. And this is something that I'd go over in the full presentation and in the paper. And then sort of this bottleneck is going to be made worse by the comparatively larger size of each DIMM when compared to DRAM, for example. And with that in mind, sort of our approach also benefits from the same cluster level parallelism. In our online recovery protocol, the TTR, or time to repair, is directly correlated with the per backup load. And what I mean by this is that our demand fetching mechanism can only handle a certain amount of per backup node and per SSD demands before like the queue depths on the SSDs increase, and correspondingly the tail latency increases. So this limit is actually quite low, on the order of say 100 queue depth. And by scaling the cluster size, in our approach, we would be able to load balance these demand fetches between different backup nodes in the cluster, as well as between SSDs within each backup node. And this would, in our approach, reduce the per backup load, and by extension, reduce TTR. So while I don't have a direct answer to this question regarding whether it's unfairly disadvantaging the comparison with RAM Cloud, I think that it's also disadvantaging our approach in a similar way. So the results are at least somewhat comparable. And I suppose on that note, evaluating our online recovery protocol on larger clusters is a big focus of our ongoing work. So thank you very much for your question.
Cool. Okay, cool, thanks. Your next question is from Anuj Kalia, who asks, the overhead of replicating to the witness node seems like it would be very high for small values. Does your design work well for values which are close in size to small keys?
Okay, so the question is basically if we have values that are the same size or smaller, for example, than the keys. In our design, we have this, what we call a witness node, and this witness node would then consume the same amount of NVMe as well as network resources as an additional primary node without providing any of the like the fault tolerance or performance benefits of adding the primary node. So that's a good observation. The overhead becomes prohibitively large, and most of the cost savings can be eliminated if you use the design that we proposed in the paper with values that are too small. But this is sort of because when we were designing our system, we assumed that the types of data sets that would be stored in NVMe for main memory class distributed storage would be dominated by sort of larger objects. So you'd have a fairly small key and then a very large object. So like I suppose data, rather than taking something that's already running in DRAM based main memory storage, you would take a workload that is currently being served from SSD and then put it into NVMe so that you can serve it at lower latency, for example. So we've received this comment a few times, and I've thought about it a lot. So I think in this case, it would necessitate sort of a change in the design of our systems, to really address the small value problem. And one of the solutions that we came up with was to eliminate the witness node and instead work on promoting a backup node to become the primary during the recovery process. And then we'd also have to rethink the indexing structures on the backup, etc., in order to reduce the memory overheads. This does come with its own challenges, but I think our key contribution, which is sort of the online recovery protocol and the key ideas behind that, it's still relevant in this case where the values are small. So I suppose the main challenge, I think, in supporting small values and promoting a backup to become the recovery primary during the recovery process would be that during our recovery process, the backup node, which has all the SSDs, is sort of the most performance critical / load sensitive component in our system. And then pushing more responsibilities onto it may result in a case where those overheads can make our protocol perform significantly worse. Thank you again for the question.
No, I agree that the pushing more responsibility to the backup node doesn't make sense in this context. But then the backup node, it already has all of the metadata that you require. So the alternate solution that you were proposing seemed to make sense to me, because I can see why the witness node makes sense in the case of a failure. But then when you have normal operation going on, Your witness node is basically just exhibiting more overhead because you have more messages flowing back and forth, right? Versus your backup node, you already have all of this metadata that you can use for free. So that seemed pretty. That's a good alternative point to consider, I guess. Is what I'm saying.
Thank you.
Cool. So while we wait for questions from Q&A, I wanted to go back to the thing we were discussing earlier, which is when we were talking about the trade-offs, right? So on a related note, I was wondering how far ahead of the actual leader selection process do you need to start your proactive recovery for it to actually be useful?
So in our experiments, the interval was roughly 500 milliseconds. Granted, we use like a shard size of 128 gigabytes in order to make sure that everything fit comfortably on the hardware that was provided to us. But I don't think necessarily that the interval between the soft timeout slash proactive recovery start and the hard timeout slash degraded mode start needs to be that long. I think it just needs to be, the longer, the more ahead we get, but it's not necessarily true that making it too short will cause the recovery protocol to fail or anything. I think it would still work.
Cool, thanks. Those were all my questions. And I guess we're at the end of the session. So we will wrap up. We're done with all 3 talks and the end of session 3. Thanks everyone for